Every shred of scientific wisdom throughout history brings us to this moment. We have never undertaken a more difficult scientific investigation. We're going to try to collide massive lead ions, atoms with their outer electrons stripped away, 200 times heavier than earlier experiments. We will accelerate these lead ions to the highest energies achievable on Earth, passing them from one accelerator to the other, each one increasing the energy of the ions. When they enter the largest accelerator ring, they will be traveling so fast, they will be a hair's breadth from reaching the speed of light.
And that's what's going on in the sun. So the electrical force is now manifest. An atom is neutral, you rip away the electrons, now you have the electrical force being manifest because you melted the atom. And if we go even hotter, 100,000 times hotter than the sun, then we get to the temperatures in which we now melt the proton or the nucleus.
When two of these tiny giants collide in the CMS detector, we expect a temperature 100,000 times hotter than the sun. A quest to understand the microcosm, a journey that began centuries ago. Preparations have a great cost in time and money. Hundreds of sensors must be set to function perfectly when the collider gets running. There could be a catastrophic failure, an explosion. It's happened before. It's like sending a probe into space. There's no room for error. It's like all journeys into the unknown. It's exciting and scary too.
Smash very dense, very heavy nuclei against each other in order to create very high temperatures, very high nuclear matter densities in order to stress the nuclear matter and then study a phase transition.
So these 200 bunches we were fine.
Yes.
We tried the same thing when we got 400 bunches. Then everything exploded.
Yes.
Well, not the detector. The HLT, so that's where the data goes through and in the end it comes out, so it's where all your triggers are coming from. And it was not coming out of there because it was taking too much time to process everything.
And of course the best part was that this was during the night.
It's this huge collaboration where really frontier physics is happening and we have collaborators from all over the world. And being able to be here today and thinking back on that day, like I have to give myself a pat on my back and be like, yes, you had an idea and somehow it worked out and you're here today.
Over 100 countries are connected and monitoring the collisions. Tens of thousands of engineers, scientists, teachers, students. Every ethnic group, every nationality working toward the same goal, carrying the flag of humanity, if you will. We are about to fire up the greatest time machine in the history of the world, becoming time travelers, going back further than ever before, to within a millionth of a second from the beginning of the universe.
Our masses go from about 20 keV.
The excitement and energy in the control room is extraordinary in a kind of slow motion way. There is fierce competition, like a car race, set up to squeeze the very best out of each team. The detector is adjusted for the different particles we are studying. We are continually tuning the trigger algorithms to harvest exactly the right data. Those few collisions among the billions that will reveal a new secret. the detectors are capable of producing an unimaginable volume of data that would crash the world's computer networks in short order.